If you have not tried this question and you are watching this video, I will highly encourage you, pause the video, stop, spoiler alert, go and try the question because this is quite the boss level question. And it'll be more fun or more challenging if you see the first time, you get stuck, you come back, do together, pause the video, go try again, and then you learn better that way. So what we have here, FM17 P22, state the principle of conservation of momentum. Well, isn't this a work energy power kind of chapter? Yes, but they can combine other topics inside also. So conservation of momentum, what is it? Initial equals to final momentum. So we are going to say the total momentum of a system is constant, or in other words, I can say the total momentum initial equals to the total momentum final. That's also acceptable. It's constant if the system is isolated. For an isolated system. For an isolated system. An isolated system really means that there are no external forces, such as friction, some field. No, we don't include those. Just two bodies interact. Then yes. These are 2 marks. Usually one will come for the first part, total constant, or this version of it, initial equals to total final. And then, this is M1, to get the last part, you must say that there are no external forces or there is an isolated system. Okay, let's go to the main part where the challenge begins. Look at this setup. You have 2 blocks A and B on a frictionless surface, joined together by a spring. Block A got mass, block B got mass. The variation with tension of extension is shown. Nice. Obeys Hooke's law. The 2 blocks are at first held apart so that the spring has an extension of 8. So you could say, maybe this one you already stretch the spring a bit further. So the spring is like, wow, very stressed already. What we need to do, show that the elastic potential energy of the spring at extension 8 is 0.48 joules. So to find EPE, there's a few ways you can do this. You could do, it's called strain energy, right? You could say find area under the graph. You could use half Fx. You could use half Kx square. They're all calculating the same thing. I think the easiest one to do would be to do half Fx. So you start from 0 origin, very nice. So just pick a point anywhere on the point where you want to pick. I think I will just choose the end point. But it doesn't really cut through the corner. I think I like this point. Let's choose this point. So, wow, let's squint our eyes a bit. This point, okay, you better do this along with me. Don't just stare at me drawing graph. You don't learn physics by watching people do physics. You learn physics by doing physics with me. So, or thinking like this. Okay, what is this? What is this value? 11, 12. So this is 12 Newton. Down there's 8. So force times distance, also known as area under the graph, which is this whole thing, half Fx is really the force times distance, force dot distance. So this one we will take half. F is 12, distance is 8. Don't forget it's cm, so must add the centi. Oh, check your axis, okay? So this value, we press our calculator, we should get 0.5 times 12 times 8 times 10 92, 0.48 joules. Proven? Yes. Very good. They give us the answer. So if you manage to find the answer, you use your half Fx, half Kx, whatever, area under the graph also can. There's 1 mark. And then you submit all the values correctly to get your final answer. That's the final accuracy mark. Now here's where the things get a little bit strange. The blocks are released from rest at the same time. So remember just now we stretched the blocks apart, now we let go. When the extension of the spring becomes 0, block A has a speed and block B has a speed. For the instant when the extension of the string becomes 0, use conservation of momentum to show that you have this interesting ratio of kinetic energy. Wow, how to start? You see, for me, if I don't know how to start, I redraw picture. So okay that's the origin picture. So we have 1 block here. Let's use black. Already stretched already. A bit far. Then you let go, you go back to, where is it? 0 extension. So maybe you come until here lah. And of course, they are both now moving at a certain speed already lor. So this one got VA, this one got VB. Before that, nobody's moving. But you do have a potential energy, which we found just now, which is 0.48 joules stored inside the spring itself. So how do we find the KE ratio? If you're not sure where to start, we know the hint they give us is use conservation of momentum. What kind of conservation momentum is this? This is the before scenario. It's like an explosion. Everybody is calm. Is there any momentum here? No. So the total momentum is 0. After you let go, wow, chaos, everybody start to move. So the total momentum final will be, okay, this is block A and B, right? Mass of A times velocity of A and mass of B times velocity of B. But remember, this is a vector, right? So I define my system. I think I'm going to choose anything that moves to the right as positive. Anything that moves to the left is negative. So this one is positive, this one negative. Okay lah, I add a negative there later. Or I could do it now. Okay, let's do it now. Plus MBVB negative. So let's just continue our conservation of momentum. So if momentum is to be conserved here, total momentum before equals to total momentum after. So 0 equals to MAVA minus MBVB. Or you can straight away shortcut and say, so the block momentum must be the same. One move to the left, one move to the right. Okay lah, can. So MAVA equals to MBVB. Oh my. Do we have masses? That is the next question. Did they give anything? Oh yes, they did. MA is 4 kg. MB is 6 kg. So 4 and 6. Okay, let's sub that in here to our equation. So this is going to be 4 VA equals to 6 VB. How is that helpful? We are kind of stuck. Never mind, we chill here first. Maybe we can use this information later. Now, kinetic energy. What is the kinetic energy? Kinetic energy is half mv squared, right? So we take the kinetic energy of A. So this is half MA. What is MA again? 4 VA squared. Do we know anything else? Not exactly. We're kind of stuck. Never mind. We continue first. Then down there for VB, half times 6 times VB squared. Oh, I see a hint. What if we rearrange the tip just now? We say, okay, so VA over VB will be 6 over 4. 6 over 4 is, why 6 over 4? 1.5, right? Yes, 1.5. So the ratio of VA over VB is 1.5. And look what we have here. VA over VB. So I can do another working here and say, okay, the half and half is cancelled out already lah. So I have 4 over 6 VA over VB and this whole thing square. So that's how we get this final value. So 4 over 6, 6 over 4 square. And this will give us a ratio of 1.5. Wow! What a working... Okay, so 1.5 is going to be, after all this, you get a ratio of KE of A over kinetic energy of B. Whew! So this final answer is 1 mark if you get 1.5. Then if you got use half mv square somewhere, I got see you know the pattern of half mv square, okay lah. Whether there or here, it doesn't matter. That will be 1, C1. And then if you got use conservation of momentum and you get something like this. Mass and velocity equals mass and velocity. That's the 1 more mark. So 3 marks for this question. Okay. So then the next part builds on this. You see this is 1 and this is 2. That means they are linked. Use the information in B1 and B2, okay, to determine the kinetic energy of block A, you can assume the spring is not moving, negligible KE, and there's no air resistance. So we only know the ratio of KE. We don't really know the exact KE. How do we start? The previous section told us that EPE is 0.48. Then once you let go, that 0.48 will all become kinetic energy. So that's a big hint. So all the EPE that you have in the beginning is converted into the kinetic energy of block A and the kinetic energy of block B as well. So we can from there write our equation already. 0.48 equals to KE of A plus KE of B. Now what? Now we probably have to use this ratio. We want to find KE of A. Yes, we want to find KE of A. So we need to get rid of KE of B. You know what? I think I'm going to do this. I'm going to write in the same color now. So from previous, we can get a ratio where the KE of A equals to 1.5 times the KE of B. That's for previous part, right? So we substitute everything in together. 0.48 joules equals to, I need to get rid of KE of B. So I'm going to keep the KE of A plus KE of B will become, it's 1 over 1.5. This will be KE of A over 1.5. Now we only have one unknown, KE of A. So finally, if we actually solve, rearrange, factorize, the kinetic energy of A will be, let me calculate, 0.288 joules. Wow, okay, so here we can write 0.288 or 0.29 is also okay. 2SF or 3SF is a must. So the final answer, 1 for here, and 1 for you recognizing the conservation of energy at work here. So any of these lines where EPE equals to the KE of both blocks, that one will be 1C, 1 mark. Oh, it's not very big brain this question. The big brain is not over yet. Got one more part at the end. Okay, let's go. So now that we have all this information, the blocks are released at time t0. Now we need to sketch a graph to show how the momentum of block A will change from time t until the extension of the string becomes 0. Is it a curve? Is it a straight line? Who knows, man? Okay, you could make a guess. Let's start by guessing. Whenever there's graph you don't know how to do, try to draw 2 dots. Is it like this, increasing? Or is momentum decreasing? So let's redraw our old block again. So your block for A, at first it is stretched. Then after a while, you will become not so stretched. So at first you are not moving, right? Release from rest, remember? That we looked at the previous section. V0. Then, suddenly you are moving at some very fast speed. What is the speed? They only give us the kinetic energy. Okay, sure. We have some velocity lah. Something. So you're moving very fast. That means your graph should start from 0 because you are not moving in the beginning and then moving very fast at the end. So it should be something like this. If you get this start and end point, that's a good start. Now, how do we know the gradient? Is it going to be a curve, a straight line, a curve, or like this? How? We think of, okay, you are moving faster and faster, but at what rate? That is the question. Since we're talking about momentum, let's go back to Newton's second law. Way back. Newton's second law said when you have a force acting on a object, that is proportional to the change in momentum over time. This is an important clue. You know why? Because when you see a dp dt or a delta p delta t, this is momentum, p against t. So this is really the gradient of the graph. So I can say whatever force is acting on my block here is related to the gradient of this graph. So if you think about the force acting on the block, there's going to be a Hooke's law force. Okay, oh sorry, wrong direction. The spring wants to pull the block this way. This force. This is F equals to Kx. Quite a big force because you got extension. But then when you come to this part here, is there a force? No more. There is no force. Because there is no extension. You got to go check here lah. The extension of the string becomes 0. There's no extension, there's no Hooke's law force 0. So from very big gradient to literally no gradient. So therefore, no gradient. And this one is large gradient. Because this is our Hooke's law. F equals Kx, and that is related to the gradient. So you draw something like this, large gradient, eventually you must get flat. And that's it. That's how you can tell your graph. So remember, step 1, what do? We find the start and end point. Just think about whether it's moving or not, because momentum is mass times velocity, right? You move, then you got momentum. Then we need more clues to think of the trend. We have to think of equations to confirm whether it's a curve or not. First mark, if your curve starts from origin and decreasing gradient, that's 1 mark. Second mark, the final gradient is 0. This is the second mark. Because eventually there is no extension, and there's no more force. No more force means no gradient, so flat. Okay, so that's one way how you can do this kind of question. There's a small add-on I would like to add. This is a bit extra, but for those of you who have learned who take maths and you want to do some advanced maths, you can actually say, Miss, can I get an actual equation? Momentum equals to something, something, something time. Yes, you can, but it involves some differential equation. So from this step, this is a side note, not required knowledge. This is outside syllabus. So if by now you're like, okay, Miss, I understand, bye-bye. Okay, then you go first lah. So I give a heads up first. This force is Kx. And this x changes with time. So I'm going to put a bracket t there to remind ourselves, oh, the x is actually changing. Then on this side, we have dp dt. So I'm going to rearrange this and say, okay, let's integrate kx that is affected by time, dt, equals to integral of just dp on the side. So I kind of split up the dp and dt. So what would I get? If I say from 0 to t and 0 to some final momentum, which we see up here, quite a high momentum, you will get an equation p equals to how to integrate this? Oh, wait, how to integrate kxt? Miss, what is the x here? Can integrate one? Okay, this one, if you have learned A2, for a object on a spring like this, the displacement actually has a very interesting shape called the cosine and sine function. So displacement actually changes depending on the amplitude, or more importantly, just for amplitude. And you start off with some extension. So I could draw a graph, some extension, and you start to oscillate. Oh, okay, extension, got initial extension here. So this will be a cos omega t. This is a snippet of A2 physics where you learn about oscillation. Preview lah. So I can substitute inside here and say, wait, my story is not done yet. Constant is k. xt is now a cos omega t dt. Then you integrate. Now you can integrate. Okay, so we get, if we use this method, integrate cos, we get a is constant. A is amplitude of the oscillation. You see this here, like wave like that. You get sine omega t, and then the omega come out. Means got intercept, but I lazy to find, so I assume don't have. So that's it. So with that, we want to see what's the relationship between P and T. You say, oh, so based on this, P is proportional to sine of T. So what we just draw here is actually one part of a sine graph. such as this one. Up, down, and up. This is our momentum against time that is also oscillating, but we only draw this part, which is what we see up there. But anyway, this is the extra thing lah, if you want to link it to some advanced maths. Well, so that's all for this video with a little further physics extension. I'll see you in the next one.